Yeah, hello, my name is Vitor. I'm currently a physics master student. And today I'm going to talk about my bachelor physics project at Tsinghua University, which is the simulation of detector response for neutron and high and intermediate energy. And to give you a rough idea, I put two images on the cover page, which is the situation that I'm dealing with, which is, you see that this is a simulation that I studied a neutron go into the scintillation detector, and it got complicated interaction. So mainly for my energy would be a kind of scattering. So this is the situation that I'm studying for the Monte Carlo simulation. And also below here would be a neutron imaging by my detector array, which is kind of an interesting result I got here after we introduced a new method. So we call microtranslation for the detector array. So I will mainly discuss some aspect of this result in the last part of my presentation. And here for the outlines, what I'm going to talk about is, first I give you some kind of introduction and a little bit basic principle of it. And I will mainly discuss the simulation of the detector unit 1, which is just a single detector I'll use to simulate. And also after we know some sort of aspect of the detector, and we'll study the detector array, which means loss of detector unit to form a detector array. In my case, would be 1600 and the simulation results, and then a summary here. And I'll give you some overview module is that, the object we're studying here would be the fast neutron in the high and intermediate energy range. And for that, their interaction, neutrons interaction is mainly depends on their energy. So in this interaction, it will be mainly the scattering and then leads to recoil nucleons so that they interact with the matter in the nucleons and then scattering for this recoil nucleus. And then for our detection, it is depend on this recoil nucleus that we just detect this neutron in the detector. And the neutron detector is the liquid scintillator here too. And then we simulate the unit and array. And the method would be Monte Carlo simulation. And we use the GM4 package developed by CERN to study this project. An introduction. And first, the neutron science here, I will first show you that it is actually quite close related to whether you say about research or industry. And why is that? Because it's unique properties. And I will list two of it. Is kind of, it is electrically neutral and if with magnetic moment, which means compared to other charged particle, like we say proton and electron, it can penetrate and go deep into our atomic nuclei, and that to see the inner structure. So it is related to our nuclear physics research, very essential. And what about application in industry? You would be kind of detection of the radiation for our security or medical or even archaeology. That's kind of radiation. So for that, you can go inside the atomic nuclei. So it would be kind of useful for this, study the detection of neutron. And to be more clarified, our fast neutron here would be in the energy unit of MeV, which is mainly the way I'm concerning here. Yeah, so when I talk about high and intermediate energy ranges, mainly we talk about the MeV level of the neutron here, which are listed in the table. And let's see about a little bit basic about the principle. As I say, this neutron interaction with the matter is mainly depend on its energy. In our energy range, especially fast neutron, which is mainly neutron scattering, which means the neutron go inside the atomic nuclei and then scatter, collide with the the nuclei. And we can use some simple, some kind of physics picture in our left frame and center of mass frame, and got some calculation, and we got the result of the maximum recoil energy, which means the neutron transfer its energy to the nuclei, and it is actually related to this relation, which means that the A is atomic mass of the nuclei. The lighter the nuclei would be got the greatest recoil energy, which what we demand for the detection for the neutron is the basis. So in this basic idea, so that we need to choose the materials for the detector. It would be in this case would be the scintillator. The scintillator consists light nuclei such as the hydrogen, deuterium, or carbon, which satisfy this requirement for the better result for our detection for the neutron. And besides the detection of neutron, if we want to do some particle imaging, besides some advanced particle imaging, which are listed here, will not be the focus for my project. I will use some kind of intuition transmission imaging method, which means you can see this image here. Like this I represent the intensity of our neutron, which is neutron beam in my case, that go through, this is whatever object and material, and then they've got some interaction, and then it will weaken its intensity as we symbolize in this arrow. And then this will be the detector, what we will detect here. So you will leave some kind of shadow in our detector, since you got here will be blocked, and then will be lower the the detector, the counts in the detector, detector, let's say array. And then in overall effect, we will see a kind of image, or you would say we use the detector as a camera. So, and it obey this exponential decrease law of this relation. The mu would be the coefficient determined by the material. The L would be the length of the material. So it is got some intuitive method to do the imaging. And the Monte Carlo simulation would be the method I use here, which require a lot of random event to to determine and to calculate the particle transport in our detector. So which I use it in our project, and it is developed by CERN, and yeah, which is the way I'm doing here by this by this tool. And let's discuss about our simulation results and some kind of setup. And I first study more about a single neutron detector unit, which is a cylinder detector with scintillation. And then I will go to a detector array. So the setup of my detector unit, as you can see here, I show you, I got a neutron gun in a simulation, and then shoot directly into our cylinder scintillation detector. And when we say scintillator, I choose two materials to study, which we call Ne213 and Ne230. It is the difference would be, the first one would be dominated by hydrogen. The second one would be dominated by nitrogen. And I study 4 sizes, which means different diameter and the length of the cylinder. And I'll see just the response of it. And a few remarks I'll give here would be, each simulation would be a million cases, since it is you've got lots of simulation data to to approach the reality to do the simulate. And also the two material, as I mentioned before, is the simulator, and got some energy points. And yeah, here I mainly do 4 parts for the detector unit. And the third and fourth one, the escape, neutron, angle, and energy will be so complicated, so which I will not include in this presentation. But instead, I would mainly talk about the first one would be the energy deposit in my detector simulation, and also a little bit more about the detection efficiency. So let's first see about the energy deposit would be something like this in my simulation. And most of the time when we're dealing with neutron detection, it would be a continuous spectrum. So in this example, it is a 10 MeV neutron get inside our detector, and this peak would be the total energy that stay with detect in our detector here. As you say, for different material, you got let's say here you got different spectrum field, and which means we got this result that we can left for further study. And you got complicated interactions, so it leads to different different peak to symbolize it, which I left some chance to study in the future. And also the detection efficiency, which means that if the energy deposit is greater than 1 MeV, and we count it as a successful detection, and then for that we can show that the percentage of detection successful count in relation with the energy of the neutron. As we expected, the higher the energy of the neutron get inside, it will get lower as it, so that I also got this detection efficiency curve for the detector unit, the single detector unit. And then after we go further study of the single detector unit, I will also study the detector array, which is something like this. I would say that in my case this would be a total of 1,600 detector units to form a detector array, or I would say a wall of it. Since we know previously some aspect of the single detector unit, so we can very surely to study the detector array in the wall. The material we choose is Ne213, which is hydrogen and carbon dominated, and the size released is here. And yeah, this a little bit more to talk about is setup here. The idea is that we just doing imaging using the principle of transmission imaging, which means we put some target area to image here, and then put the material between the neutron source and the detector array. And then one important factor would be our neutron source should be inject isotropically, which means it should be cover the whole array, the wall. And yeah, and we just change alter our materials of this that we want to do the imaging. And yeah, this is the material we just do in the simulation. There's got some simple sphere and also some blocks with some holes, as I list here. As you can see, we can see the combination of different results here. A little bit remarks would be that, again, this would be a million cases. So it needs that amount of simulation data to, is the basis of the Monte Carlo simulation. And the material, as I mentioned before, is Ne213. And yeah, this again is a fast neutron imaging. And we got two methods. The first one would be the directly use it as a single pixel. And the other one would be our new method that I will introduce. And let's first see the directly pixel result. It's here. This would be for the 14 MeV, the directly result of neutron imaging. This image is a contour image, which means the yellow color would be the more of the current, the effective current, and the blue color would be the lower the current of the detector, as it can visualize quite intuitively for the transmission imaging here. As you can see, mostly directly use it would be okay from 3 cm, but below the 2 cm, it can be more improvement. And at the same case with the 5 MeV neutron, but the contrast, as you can see, is better than the 14 MeV, which means the 14 MeV is penetrate more greater. And here would be another result of our directly used pixel of the blocks with holes and of the blocks with some words here. And I first introduced monolithic microtranslation movement, which the basic idea would be instead of, we want to improve the resolution. Instead of we just make it smaller, we just move it, translate it in a hole. And let's take an example of this. Originally it is a cylinder. In a 2D projection would be a circle. And then in our imaging result, it would be a rectangle with 5 cm as 1 pixel. And now we just divide it into 1 cm per each movement translation. Let's take example of if we move right-hand side, it would be, if we move right-hand side, we can move 2 times, and then the center of the rectangle would be reach the boundary. So let's demonstrate it like we move first time here, and then we move second time here, and then you reach the boundary. And the same applied for the, the left-hand side and the upward and the downwards. And also the combination of these 4 corners. So to combine it, we just translate it as a whole, and then you will list the, the pixel would be 1 cm. And that it can ideally improve the resolution and the sharpness. And then we can see the result here. We improve it from the 40 times 40 to the 200 times 200, which is quite an interesting result as we, in the calculation, also for the blocks and also for our blocks with the host of works. So, which means that we demonstrate this, prediction about our neutron imaging by this method here. And in summary, I talk about a little bit background of the research of neutron detection, some interaction, and my interesting result about detector unit 1 and detector array response. And yeah, that would be the end of the presentation. Thanks.